Well, welcome back to our course on algorithms and data structure. So we're going to be continuing on in this section that we're talking about BAG. And so we talked about the BAG, we talked about BAG implementation, and then we had a Java interlude, and now we're going to do another discussion on BAG implementation that links to data. So this is another interesting area that we'll want to make sure that we're familiar with. So here's what's going to be covered in this textbook chapter. And so we'll first talk about linked data, forming a chain by adding it to its beginning. And then we'll have various ways of doing linked implementation of the ADT bag. We'll talk about removing an item from a linked list. And we'll then talk about a class node that has set and get methods. And finally, a summary of the pros and cons of using a chain to implement the ADT bag. So using an array to implement the ADT bag has both advantages and disadvantages, as we saw before. An array has a fixed size, and so it can either become full or have several unused elements. You can resize an array when it becomes full by moving its entries to a larger array, although resizing an array can provide as much space as a bag needs. You must move data each time you expand the array. So in this chapter, we're going to introduce a data organization that uses memory only as needed for a new entry and returns the unneeded memory to the system after an entry is removed. By linking data, this new organization avoids moving data when adding or removing bag entries. These features make this way of implementing a bag an important alternative to array-based approaches. So this is just a reminder. We talked about this before, but what is an iterator? And so it's an object that traverses a collection of data. During iteration, each data item is considered once, and it should implement as a distinct class that interacts with the ADT. So how would you count the number of lines on a page? We talked about this before. You could use your finger to point at each line as you counted it. And so that would be one way. So you're traversing through the whole page. Your finger would keep your place on the page. If you pause at a particular line, your finger would be on the current line, and then you would be previous line and the next line before and after that. If you think of a page as a list of lines, then you would be traversing this list as you counted the lines. And the iterator enables you to step through or traverse a collection of data such as a list beginning with the first entry. During one complete traversal or iteration, each data item is considered once. You control the progress of iteration by repeatedly asking the iterator to give you the reference to the next entry in the collection. You can also modify the collection as you traverse it by adding, removing, or simply changing entries. So that's some things that we'll be utilizing as we get into this lecture and this chapter. So what are some of the problems with array implementation? They have fixed size, they may become full. Alternatively, they may have wasted space, and resizing is possible but requires overhead. So those are all things that we want to be mindful of, the finite size. And there's also another problem with an array-based implementation is the shifting arrays entries that often occurs. So why don't we think in terms of an analogy to try and help us get familiar with this? And so here in the figure, we're seeing a chain of 5 desks, no desk references, the first desk in the chains, but the instructor knows its desk number, 22. Notice that the last desk in the chain does not reference another desk. The piece of paper on the desk is blank. The chain of a desk provides an order for the desk. Suppose that the first in the chain is the student who arrived most recently. Written on the student's desk is the desk number of the student who arrived just before. All but one student sits at a desk that references that desk of the student who arrived just before. The one student arrived first and sits at the last desk. So the last desk does not reference another desk. the instructor knows the address of the first desk in the chain, and so can ask questions of the student at that first desk. Then by looking at the address or desk number that is written on the paper on the first desk, the instructor can locate the second desk in the chain and can question its occupant. Continuing in this way, the instructor can visit every desk in the order in which it appears in the chain. Ultimately, the instructor reaches the last desk in the chain, which references no other desks. Note that the only way the instructor can locate the student in the last desk is to begin at the first desk. Also note that the instructor can traverse this chain in only one order. In our simple example that we talked about before, with the instructor in room A, the instructor was able to ask questions of any student in any order. So anyways, we're getting a chance to see how this might work. Okay, what about forming a chain by adding to its beginning? So how did we form the chain of desks in the first place? Let's return to the time when the room L was empty and available desks were in the hallway. Suppose that Matt arrives first. He gets a desk from the hallway and enters the room. The instructor notes Matt's desk number, address, and we leave the paper on the desk blank to indicate that no other student has arrived. The room appears in the first figure, 3-2, that you're seeing up in the corner. And that process continues with more and more students. So here we're showing the pseudocode details of the steps taken to form a change of a desk by adding each new desk to the beginning of the chain. So once again, this course is data structures and algorithms. And so the pseudocode is trying to give us a more general way of talking about the algorithm. Let's talk about the private class node. We begin by defining a class of objects called the nodes that represent our Java equivalent of desks. We typically link nodes together to form a data structure. Our particular node have two data fields each, one to reference a piece of data, presently an entry in a bag, and one to reference another node. An entry in the bag is analogous to a person who sits at a desk. The reference to another node is analogous to the address written on the paper that is on each desk. So the figure here illustrates two nodes that are linked and contains reference to the object in the bag. So here we're seeing an outline of the class linked bag. And so for this implementation of the ADT bag, we will use a chain of linked nodes to contain the bag's entries. In our earlier classroom example, the instructor remembered the address of the first desk in a chain of desks. Similarly, our implementation must, quote, remember the address of the first node in a chain of nodes. We use a data field called the head reference to record a reference to that first node. A second data field can track the number of entries in the bag, that is the number of nodes in the chain. So in the listing, it contains an outline of the class link bag that implements ADT bag. It contains the class node as an inner class. Recall that chapter 1 introduced the interface bag interface, and the classes that implement it define a generic type for the objects in a bag. The identifier T that we use for this generic type must match the one that we use within the inner class node. So anyway, so this is just continuing on. And then here in the figure, we have illustrates two steps here. The part A of the figure shows the empty chain and the node created by the first statement. And then part B shows the result of the second statement. Note that in part B, both the first node and the new node reference the same node. After the insertion of the new node is complete, only first node should be reference it. We should set new node to null, but as you will see shortly, new node is a local variable of the method add. As such, new node will not exist after add ends in its execution. The same is true of the local parameters new entry, which behaves like a local variable. So we make the new node reference the first node in the chain, making it the first new node. And so in this figure, we're illustrating the steps in the following Java statements implement them. And so here is where we're starting to show those the Java. And so here we're seeing the method add. And so as you have seen, although it might appear that an empty bag is a special case when adding a new entry to a bag, it really is not. And so we have the following definition of the method add that uses this conclusion. And so here we're laying out the code for the method add. So let's move on to the method toArray. The method toArray returns an array of the entries currently in a bag. By implementing this method, we will be able to test whether the add method works before we complete the rest of the class linked bag. To access the bag's entries, we need to access each node in a chain, beginning with the first node one. This action is called a traversal, and it is analogous to visiting each desk in a chain of desks as we described before. The data field first node contains a reference to the first node in the chain. The node contains a reference to the second node in the chain, and the second node contains a reference to the third node, and so on. To traverse the chain, the method toArray needs a temporary local variable current node to reference each node in turn. When current node references the node whose data we want to access, that data is at current node data. Initially, we want current node to reference the first node in the chain, so we set it to first node. After accessing the data at the current node data, we move to the next node by executing current node equals current node dot next. We again access the data at current node data and then move the current node by executing current node equals current node next dot next. Once again, we continue in this manner until we reach the last node and current node becomes null, and the following method toArray uses these ideas, and we have them listed here in the chart. So then we have a test program, and so a driver program that you can use all of this. And so a test program for link bag 1 could be like the one for array bag as given before in the previous chapter, except for the name. The class used to create a bag and one other significant distinction. Although an instance of array bag can become full, an instance of link bag will not. And so here in the listing, it outlines such a test program. Notice that the private static methods here are exactly the same as those given in when we were talking about related stuff in chapter 2. This is possible because the methods use bag interface as a data type of a bag. So this is the first part. This is the second part, and I won't go through that, but it's here for completeness. And then here's the third part. And finally, we have the end of it and also the data output. And this is something that we can show using Eclipse, which is what the textbook refers to as a good integrated development environment to play some of this out. And some of this code is made available. And so we'll get a chance to look at that outside of this recorded lecture. Okay, let's look at a couple of methods. And the first is the get frequency of. To count the number of times a given entry appears in a bag, we must traverse the chain of nodes and look at the entry at each one. The traversal is much like the one we used in the method toArray. Thus, if current node will reference the node that we want to examine, we set it initially to first node, the first node in the chain, and then use the statement. Moving on to the method contains, as in the previous chapter, when we use an array to represent the bag's entries, we learn when a bag contains a given entry by examining each array element starting at index 0 until we either found the desired entry or discovered that it was not in the array. We use an analogous approach here to search a chain for a particular piece of data by looking at the chain's nodes one at a time. we begin at the first node, and if that does not contain the entry we are seeking, we look at the second node and so on. When searching an array, we use an index to search a chain. We use a reference to a node. So just as in the method get frequency of, we use a local variable current node to reference the node that we want to examine. Initially, we set current node to first node and then to current node dot next as we traverse the chain. However, instead of traversing the entire chain like get frequency of does, we loop. Our loop iterates until either we find the desired entry or current node becomes null, in which case the entry is not in the bag. Here is a discussion on removing an item from a linked chain. And so there's a couple possibilities, and we'll take them one at a time. So earlier in the chapter, we looked at the analogy of a classroom to describe how to form a linked chain of data. Available desks are in the hallway outside of the classroom. Each desk has a number, which correlates to an address, a memory address, stamped on the back, and a blank piece of paper taped to the desktop. As students enter the room, they take a desk from the hall. We write on the desk, the new desk piece of paper, the number of another desk already in the room, and give the instructor the new desk number. In this way, the desks are linked to one another, forming a chain of desks, as we saw before in a figure. So no desk reference the first desk in the chain, but the instructor knows its address. The last desk does not reference another desk. Its paper is blank. Students who leave our classroom, room L, return their desk to the hall. Such desks can be rearranged to reassigned to other students who enter either room L or other rooms that share this hallway. Suppose that you are a student in room L, but you want to drop the course. If you simply move your desk to the hallway, you will not actually remove yourselves from the chain of desks in the room. Either another desk or the instructor will still reference your desk. We need to disconnect your desk from the chain. The details of how we do this depends on where your desk is in the chain. And so there's two possible cases: that your desk is first in the chain of desks, and the second case is your desk is not the first chain of desk. So for case one, here we see in the figure, it illustrates case one before we remove the desk from the chain, and the following steps are necessary to remove the desk. We'll talk about it, and first we locate the first desk by asking the instructor for its address, and we give the address that is written on the first desk to the instructor. This is the address of the second desk in the chain. And then we return the first desk to the hallway. Figure 9 shows the chain after the first two steps taking place. Notice that the first desk is no longer part of the chain. Technically, it still references the second desk, but if the desk is empty, is ever used again, a new address will be written on its paper. So that's the first case. Here's an illustration of the remove and clear, the methods that we would be using. So the moving an unspecified entry, that the method removes without a parameter, removes an unspecified entry from a bag that is not empty, according to the method specification as given in the interface in listing 1.1 of chapter 1. The method returns the entry it removes. And so we talked about that in a previous chapter. The bag is empty before the method executes, null is returned. Removing an entry from a bag involves removing it from a chain of linked nodes. Since the first node is easy to remove from the chain, we can define remove so that it removes the entry in the first node. To do this, we take the following steps: accessing the entry in the first node so it can be returned, and then set the node to the reference to the second node, as shown in figure 310 indicates. And if a second node does not exist, we set the first node to null. Okay, here's the second case. So remember that a bag does not order its entries in any particular way. This our analogous classroom, we assume that the students are seated in no particular order. we want to drop the course and are not seating in the first desk in the chain, we do not have to remove your desk. Instead, we take the following steps. Move the student in the first desk to your former desk, remove the desk, the first desk using the steps described for case 1. In effect, we have changed case 2 to case 1, which we know how to handle. So that's a simple way to use previously developed material. So here is the Java code for remove. And it also includes the method get reference to. And from that, we have the methods remove and clear. So we're moving an unspecified entry. The method remove without a parameter removes an unspecified entry from a bag that is not empty according to the method specification as given to the interface in listing 1-1 of chapter 1. And the method returns the entry it removes. And so here we're seeing that. So I think, let me just, on this previous chart, the way that it does the remove is by using the method get reference to for starters. So we talked about this and the method clear. If the bag is empty before the method executes, the null is returned. Removing an entry from bag involves removing it from a chain of linked nodes. Since the first node is easy to remove from the chain, we can define remove so that it removes the entry in the first node. And to do so, we take the following steps. Access the entry in the first node so it can be returned, set the first node to reference to the second node. If the second node does not exist, set first node to null, decrement number 1 entries. And you would want to notice that how we implement these steps in the following Java definition of remove, and we'll get to that in the next chart. So clear is a fairly straightforward method, and basically you remove each one, and first of all you check to see if it is empty and so forth. So here is the code. The class node that sets and the set and get method. So because node is an inner class of the class of linked bag can access node's private data fields directly by name. Doing so makes the implementation somewhat easier to write, read, and understand, particularly for novice Java programmers. However, you really should access the class data fields only by calling accessors and muters, that is get, the set and get methods. In fact, we will do so in the rest of the book. This section adds these methods to node and explores 3 ways to define the classes. As an inner class, suppose that we add the methods get data, set data, get next node, and set next node to the inner class node, as it appears in listing 3.1. The class would then appear as given here in the listing. So here's a class with a package. And so after we modify node and link bag as just described, node could remain as a private inner class since node is an implementation detail that we want to hide, making it an inner class as appropriate. But if we ever changed our minds and wanted to define node outside of link bag, we could do so while retaining the modifications to link bag made in the previous previous segment. So we could, with a few changes, make node accessible only within a package, or we could even make it a public class. To transform node as given in listing here 3.4 into a class accessible only by other classes in its package, you first omit all of the access modifiers except the ones for the data fields. You then add T after each occurrence of a node within the class definition, except when it is used as a constructor name. The revised class appears in listing 3.5, and which we're showing here with that T notation. So the class link bag can access node as given in listing 3.5. In both classes, they are in the same package, and we modify link bag slightly. Each occurrence of the node within link bag must now appear as a node T. We begin to make these changes to the link bag and highlight them and listing 3.6 as we're starting to show here. So let's talk about the pros and cons of using a chain. So first, you're looking at the pros, and then we'll get to the cons in the next chart. But you have seen how to use a chain in implementation of the ADT bag. One of the greatest advantages of this approach is that the chain and therefore the bag can grow and shrink in size as necessary as long as memory is available. You can add as many nodes to a chain as you wish. Moreover, you can remove and recycle nodes that are no longer needed. Although you can resize an array to allow a bag to grow in size, as the previous chapter describes, each time a larger array is necessary, you must copy the entries from the full array to the new array. No such copying is required when you use a chain. So that's a starter here. And as you're looking at the pros, we'll get into the cons, and we started really to begin to talk about that. Adding a new entry to the end of the array or to the beginning of a chain are both relatively simple tasks. Both operations are fast unless the array needs to be resized. Likewise, removing the entry at the end of an array or the beginning of a chain takes about the same effort. However, removing a specific entry requires a search of the array or chain. Lastly, a chain requires more memory than an array of the same length. Although both data structures contain references to data objects, each node in the chain also contains a reference to another node. However, an array is often larger than necessary, so memory is wasted. A chain uses memory only as needed. Okay, that's going to be it for our lecture here on chapter 3. Thank you very much.